One other thing I wanted to spend a little bit of time talking about is considerations in the timing of logic gates. So just like how you have to worry about, potentially have to worry about the current flowing in and out of them, you also have to worry about when these output values are changing relative to the inputs, because that does not happen instantaneously. So, it should go without saying, but in case you didn't think about it, changes in the input cause changes in the output, and those changes in the output always happen sometime after changes in the input, right? They can't happen before. There's some like causality sorts of things. So in other words, if I have an inverter gate and I change this voltage at time t equals 0, I send some signal to this, I turn it on or off. The output that I get here does not change at time t equals 0. It changes at some time t greater than 0, right? And how fast this happens depends on some details about what's going on here. In particular, what flavor of logic device this is, CMOS versus TTL, and also which family it falls into. You can look up more information on that if you want, logic families. And it also depends as well to some degree on how much voltage you're using as this different logic families. Some of them you can have working at some of them work at different voltages, and so they're going to give you different behavior at those different voltages. So typical delay values are going to be between 1 to 10 nanoseconds. So that's billionths of a second, so 10 to the minus 9 seconds. To illustrate the range of different propagation delays, here's a figure from the 3rd edition of The Art of Electronics by Horowitz and Hill, showing propagation delay, so the time delay for the gates on the y-axis, and power dissipation at 1 megahertz switching on the x-axis for a bunch of different logic families. And you can see some of them are CMOS and some of them are TTL. If you're doing anything fast enough to be pushing those limits, you're gonna have to learn more detail about this anyway. So I'm not too worried about filling you in on 100% of the details here. So the sorts of things that matter here are like, let's say I have a signal that goes into this gate and comes out, and then I send this somewhere else. And let's say I have this happen another place also, right? I'm sending some different signal to this, and that's going somewhere over here. And these are both going into the same system. So if I change both of these at exactly the same time, so these are not going to just change at the same time as these inputs. These also may not change at the same time as each other. These two gates might have slightly different delays for whatever reason. And so you can't always rely on these signals arriving at the same time. That can lead to problems known as race condition errors, where it's like the two signals are racing to get there at the same time. So anyway, so that's the sort of thing you have to be concerned about. Electrical signals travel at a little slower than the speed of light through typical wires. And the speed of light is roughly 1 foot per nanosecond. So this also leads to one other thing. If we're talking about a delay of, a nanosecond here from this gate, that's also similar to the timing difference you expect for a signal to travel through 1 foot of wire, or even a little less. So what that means is if you're looking at these, small differences in timing, not only do the gates themselves make a difference, but the geometry and like how long your wires are can make a difference too. So anyway, these problems can get complicated, and there are entire classes about this. So we're only barely scratching the surface of this concept. Okay, so in general, this is a problem you have to contend with when designing circuits that operate at high speed or with short delays, measuring short delays. You can also use this behavior to your advantage, and I'll show you one example of this. So let's say we have a clock. I'm just going to give you kind of an example circuit that does something kind of fun. So I have a clock circuit that goes into an AND gate, And the other input to the AND gate also comes from the clock, but before going to the AND gate, it goes through an inverter and another inverter and another inverter. So these are all our not gates, or our variable inverters. Okay, so we're going to call these. I'm just going to name these points so we can talk about them. This is 1, this is 2, and this is 3. Okay, so before we learned about delays, if we were taking this naive, very mathematical look at what's going on here, you can analyze the circuit and say that our output is always going to be off, right? Because if the clock is on and the AND input here is on, well, that gets inverted to off, which gets inverted to on, which gets inverted to off. So anytime this is on, this has to be off, but they both need to be on to get the output on. So the output is always going to be off. That's what we would have said last week or whatever. Okay, but once we take these delays into account, this isn't true anymore, and there's something cool that happens because of it. So let's draw a timing diagram of what does happen. So here's our clock signal. So it looks like this. We'll say it starts out low, and it turns on. So let's plot what's going on at points 1 and 2 and 3. So at point 1, if the clock has been off, point 1 is going to be on. And then when the clock turns on, point 1 turns off, but it doesn't do it right away, right? A week ago we would have said this graph looks like this, right? It turns off at exactly the same time, but we know this isn't true. We know there's a delay that happens because of this gate. And so what we end up with is something that looks more like this, where this is our, sorry, we'll only draw it to here, where this delay is whatever happens because of our gate. Let's just say that these are 10 nanosecond delays. So this time here on this graph is 10 nanoseconds. Okay, well, the output of the point 1, which is the output of this first gate, is the input to the next one. So point 2 is going to be the inverse of point 1. But again, instead of switching instantaneously, there is also going to be another delay. So this is another 10 nanoseconds. And the same thing happens at point 3. It turns off after that 10 nanosecond delay. When this then turns off, 1 turns on slightly after that, 2 turns off slightly after that, and 3 turns on slightly after that. Okay. So what happens at the input to the AND gate? So this is the clock and 3, right? So these are the things we're interested in. So the output graph looks like this. The clock is off this whole time, so the output has to be off that whole time. When the clock turns on, 3 is on. So where this happens here, I want to keep this lined up, our output actually turns on. Sorry, wait. Oh, right. Okay, so I thought there was an error, but the error is up here. So there's another delay also, because when the clock and 3 both give this the on input, that would happen right here, except there also is a delay from the AND gate. So there's another 10 millisecond delay that happens here before this turns on. So really, so it turns on when the clock turns on, except we have to add this delay for the AND gate. Okay, so then it's going to stay on until the clock or 3 turns off. So the clock stays on for a long time. 3 stays on for, 3 is on for 30 nanoseconds after the clock turns on. So we have something that looks like this, where this whole time is 30 nanoseconds, and then it turns off. And over here, you can see that the clock is off when 3 turns back on, so there is no second pulse. Anyway, so the point is, this clock switches on and off at some slow speed. This could be, switching on and off every millisecond or many milliseconds or something like that. The clock can be something slow, but it can generate these very short pulses. The size of this pulse is determined by the delay of the gate, not how fast we're switching the clock on and off. So this is kind of a trick you can use to make very short electronic pulses. One other thing that this is used for is what's called a ring oscillator. So if you take a bunch of, I guess I can erase this, yeah. The idea of a ring oscillator is if you have an inverter gate, so our NOT gate, and you connect a few of them in series together, like we just saw. If you connect an odd number of them together, it turns out that the input and the output are always going to want to be different, but you can still connect them together. So you can make something that looks like this. So if this starts out, let's say this starts out off, that means this is going to invert that to be on, which gets inverted to off, which gets inverted to on, which gets inverted to off, which gets inverted to on, and turns this on, and that changes down the whole row again. So anyway, you get all of the points in this circuit are oscillating between on and off, and they're oscillating at a frequency that depends on what the delay is of these different gates. So ring oscillators, they're not really great to use as frequency sources because they're unstable and depend on the details of this, but they can be a good way if you're in the manufacturing business and you want to characterize how well your gates work. You can make ring oscillators because it's easy to measure frequency and how compare that to the frequencies you expect, and use that to assess if the inverter gates or whatever you've made are functioning the way they're supposed to be. So it's kind of a quick and dirty way of measuring a few of these gates at once and assessing their quality as logic gates. Yeah, so this is just a fun thing. You can show pretty easily that this circuit has no stable state, so it's going to oscillate on and off indefinitely.